As we continue our treatment of Newton's law of universal gravitation, you'll recall that in the previous video I mentioned that if you had a couple of symmetric objects interacting gravitationally, circular symmetric objects that were interacting gravitationally, you could treat them as if they were point masses located at their center. But I didn't prove that yet at the time. I'm going to work towards giving a sketch of a proof here. Now, to start, one of the things we have to realize is that gravity is said to obey superposition, which seems like a really fancy word. What it means is it's one of those things that's like almost too obvious, but sometimes you have to state it out loud. Let's say I had three 1 kilogram objects. Oops. 1 kilogram, 1 kilogram, 1 kilogram. Let's say this distance is a meter. That distance is a meter. What I want to find is the gravitational force that these two objects exert on this one. Now, the miracle of superposition is that what I can first do is pretend that these two objects are the only two in the universe and figure out the gravitational force due to this one. So let's call that object number 1. This is FG1. And then I say that this object and this object, we'll call this one object 3, I guess. Object 2 here. We'll pretend that objects 2 and 3 now are the only two objects in the universe. And we'll find the force of gravity due to object number 2, FG2. That's going to be a bad place to put it. We'll just do this, FG2. There we go. Then what you can do is you can take the vector sum of the two, and that is the gravitational force that that object feels. It's one of those things where you look at it and you say, how could it possibly be any other way? But it's not obvious that it has to be that way. It could be, for instance, that for some reason we always had to consider object 1 and then object 2, or we had to consider them all together somehow or something like that. But we don't have to. It turns out that we can first pretend that objects 1 and 3 are the only two in the universe, and then objects 1 and 2. So just to flesh this out with some numbers, the force of gravity from object 1, its magnitude, is going to be G m1 m3 over r squared, where r is that 1 meter right there. So this will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We'll be times this by 1 kilogram times 1 kilogram over 1 meter squared. All right, so I don't think it comes as any surprise that that's 6.67 times 10 to the negative 11 newtons. Similarly for FG2, that'll be G m2 m3 over r squared. And honestly, I am just going to copy and paste this bit. There we go. And then to get the net, we'll have to do the vector sum. Now, conveniently, I rigged this up so these were perpendicular. So we can just use the Pythagorean theorem in this case to get our total gravitational force. So Fg would be the square root of Fg1 squared plus Fg2 squared. So that'll be our 6.67 times 10 to the negative 11 newtons squared plus the same sign. And you'll get 9.43 times 10 to the negative 11 newtons, which isn't a lot. That's why in the Cavendish balance experiment, typically your separations are as small as you can possibly make them, and even so, it is a very sensitive, very fussy experiment. But that's how you would do it. And if you had more than two sources, you would just keep on going. If you had another one over here, you would just pretend this one and this one were the only two in the world, add that into what you had already. Keep in mind, you got to do this a vector sum. All right, so with that in play, we can start doing the first part of the Shell theorem, which says, here we go. Oops. Try that again. There. So the Shell theorem says that this is the center of mass here. And this is, we'll say, MA. And this is our distance R. The first part of the Shell theorem says that outside, yeah, I can spell today, outside of a uniform shell, spherical shell, you can treat the shell as a point mass located at its center. I won't prove it, so I'll just give you a sketch of how it's done. It's similar in vein to those integrations I was referring to for locating centers of mass in the first place. So the idea is you pick a piece of your shell here, say this little piece right here, and it's of differential size. So that's your mass dm. We'll say that this is radius r sub shell. We'll call this distance here little r, because that's what that is there. And then the distance that matters for finding the force of gravity is going to be this distance here, big R, which by the law of cosines, if this angle is phi, is going to be equal to the square root of r squared plus rs squared minus rrs cosine phi. And this will give us a differential contribution of the gravitational force F sub G, D, F sub G, like that. And what you'll realize is that the only piece of it that's going to matter is the x component of it. And this is because the vertical component and the in and out component, the y and z, will cancel out once we integrate over all of the masses. Because for this one, there'll be a matching one down here, where it would pull down exactly, down and left is exactly the same strength and angle as the up and left here. So we'll call this angle here theta, and you get that is going to be g times our differential mass dm times ma over big R squared cosine theta. Now this theta does actually depend on phi, so you're going to have to invoke the law of cosines a second time, do a whole bunch of stuff, and I'm just going to say integrate this. At the end, what you get is that the x component of the force of gravity, which, since it's just directed along the x direction, is equal to g times the mass of the shell times our test mass ma here over little r squared. So I'm just going to assert that this happens The integration is insanely tedious and annoying, but I have done it elsewhere in the channel. So anyway, you look at this and say, zounds, this looks exactly like I had 2 point masses, one located here at the center of mass, one located there. And that's how we get that result. The second part of it is if you are inside the shell. Oops. My bad. There we go. So if you are inside the shell, the net force of gravity due to the shell is 0. And again, you have to set up the exact same sort of tedious integration. But I think I can, at least when I put this down here, if I look here and imagine dividing it top-bottom like this, you can say, oh, for every piece on top, there's a matching piece on bottom. I can see how the vertical pieces cancel. And same with in and out of the screen, you could imagine the same thing. What's maybe a little trickier is trying to figure out what's happening here when we divide it right-left through the mass here. So it turns out that there's less mass here, but it's closer. So each little bit of mass pulls harder on a mass there. Here there's more mass, but it's on average farther away. And oddly enough, the mass versus the distance thing balances out perfectly, and you wind up getting that even in the x direction here, the gravitational force cancels out. Strange but true. All right. So what this means is that, say, if you are out, so now our next corollary to this is if we have any spherically symmetric object. Let's try that again. There we go. So we have any spherically symmetric object. So let's say this is solid somehow. And as long as the density at every depth is the same, we can even change how much the density is, just as long as it's purely a function of radius. Outside, you can think of this, you can still treat, so if I'm here, I can still treat as a point mass. And this is because I can think of this as a whole collection of nested shells. But if I'm inside of it, then what I have to do, so let's say my point of interest is right here. I have to think about the spherical shell that just happens to go through the point of interest. And so I'm inside all the shells that are bigger radius than that, so I'll crosshatch those in black. And so effectively, these shells don't count. And that's because you're inside of our nested set of shells here. And if you're inside a shell, the net gravitational force is 0. So the bit that I'm cross-hatching here in red, this is the mass that counts. And again, we can treat it as a point mass located at the center. So in the dead center of the Earth, the gravitational force of the Earth on anything is 0. And you can actually show that it increases steadily as you get to the surface of the Earth. And then once you're outside the surface of the Earth, it falls off as 1 over r squared, which is what we saw before. All right. So now with that, let's get into why it's called Newton's law of universal gravitation. And this is where we'll consider gravity near the Earth's surface. So, or any planet, but we'll just use the Earth. So here's the Earth. So that's the radius of the Earth right there. Let's say I'm standing here on the surface of the Earth. Now, I wish, my ego would wish that I was this big, but realistically, the distance my center is from the center of the Earth is about 1 meter more than the radius of the Earth, which is already a really big number. So we can say that the distance from the middle of me to the middle of the Earth is pretty much just the radius of the Earth. This is going to affect things in literally the 6th decimal place. And then we're going to be squaring it. So that means we're affecting things in the 12th decimal place. So it really isn't going to matter. So what we can do is we can say, all right, the gravitational force on me here is going to be g times the mass of the Earth times my mass over r squared. And we'll go ahead and say, let me pull the m out like this. And we'll say that this is basically the same difference as g times the mass of the Earth over the radius of the Earth squared. Because remember, this is the radius of the difference between the center of the Earth to me versus the center of the Earth to the surface of the Earth is 1 meter. So that's showing up in about the 6th decimal place. And then with this squared, you can see things are it's going to affect things along like the 12th decimal place. So not a big deal. Let's give this a name. I don't know. Little g sounds good to me. So this is our gravitational field strength. Let's calculate it. So this will be g times the mass of the Earth over the radius of the Earth squared. So this will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.974 times 10 to the 24 kilograms. And the radius of the Earth is 78,000 meters. I think I got that right. I do not have that right, actually. All right, fine. The diameter of the Earth is 12,756,000 meters. I remember that one off the top of my head. Divide by 2, square it. Anyway, punch it through your calculator. You get 9.8 newtons per kilogram. And so that's what it is near the surface of the Earth. Now, if I'm far enough, eventually I will get far enough away that that I can't just say that the r is approximately the distance from the surface of the Earth. So in that case, let's say I'm sitting up at some height h above the Earth. So again, this is the radius of the Earth. That's going to make this radius here, between the middle of me and the middle of the Earth, r will be equal to the radius of the Earth plus h. Okay. So then g, we saw, this will change this. G will now be equal to big G times the mass of the Earth over the radius of the Earth plus h squared. All right. Now there's a trick we can do here. I want to get this into a form that looks like the G we had before on the surface of the Earth. And I can do that if I pull a radius of the Earth out of both of these. So I'm about to do that. This is G, mass of the Earth, radius of the Earth squared times 1 plus h over the radius of the Earth squared. Oops, sorry. Radius of the Earth quantity squared. Now this bit right here is G on the surface of the Earth. And this will be 1 plus h over the radius of the Earth squared. And honestly, it's not a big deal pretty much anywhere where anything can breathe air. You, a machine, whatever. I mean, at the altitude of a jet aircraft, you're down less than 1/3% off of the surface of the Earth. When you get to the altitude of the International Space Station, about 300 kilometers, then it starts to become a big deal. You'll get 8.9 newtons per kilogram instead of 9.8, and so forth. And the farther away you get from the surface of the Earth, the weaker the gravitational field strength becomes. So in the next video, we'll go ahead and take a look at the potential energy and think a bit about orbital dynamics. Catch you over there.